So welcome back. This is our second video about graph decomposition, and we're gonna continue discussing elimination orders. And the idea now is to try to find out some techniques to find good elimination orders with less time. So the problem of finding an optimal elimination order is NP hard. So there is a typo here. It is NP hard. So the way that we typically deal with this problem is using some heuristics. So the idea is that we can use a grid algorithm that will compute the elimination order. This algorithm is not optimal, but it is frequently good enough and will provide some good elimination orders. The elimination orders will not be optimal, but they will be typically good ones. And there are two heuristics that are very common. One is called mean degree, and the other one is called mean fill. And the mean degree is basically choose to be the next node to be eliminated, the node with the smallest number of neighbors. And the mean fill heuristic, it says that the next node to be eliminated is the node that introduces the smallest amount of filling edges. And typically people find that the mean fill heuristic provide better results than the mean degree, but we also know that the mean degree heuristic is optimal for graphs with tree width that is less or equal to 2. So what it means is that if we have a very simple graph that has a very small tree width, so the mean degree heuristic will be able to find the optimal elimination order for this graph. What I usually note is that typically when we have this graph representation and we look at that, it's a lot easier to find out what are the degrees of the nodes than the number of filling edge that will be introduced. So using C as one example, we can easily see that C has 4 neighbors, and the degree of C is 4, so it's very easy to compute. And in this case, if we are considering the mean fill, the mean degree heuristic, C is not as good as B because B has 3 neighbors instead of 4. So in this case, we will prefer nodes like B and D that have a smaller number of neighbors. But if you want to compute, so it should be clear, that's just me erasing this, so it should be clear that it's very easy to find out what is the degree of the nodes, but if we want to calculate what's going to be the number of filling edges that will be introduced, is a little bit more complicated because we have to do a small process of simulation. So in the case for C, what's the number of filling edges that C will introduce in the case that we remove C? So we need to see which are the neighbors of C that are not connected by one edge. So we have like A and B. They are neighbors, but they are also connected already, so they will not generate a filling edge. We have A and E that are neighbors, but they also have a filling edge. We have also E and D, also neighbors of C, but they have a filling edge. And now we need to consider other possible combinations like B you have here and E. They also have a filling edge, so no problem here. And we also have A and D. They also have a filling edge. So what is missing here is a filling edge between D and B. So we have here B and we have here D, but we don't have a filling edge connecting here. So the mean fill score of C will be 1, that is this missing edge between B and D. And we have to do this for every node. So that's is the mean fill score for C, it's 1. If we can find another node that has a mean fill score of 0, that node should be eliminated before C, and that is the idea. And it's very common in practice to combine heuristics in order to get even better results. Because mean fill is a heuristic that tends to provide better results than mean degree, what people usually do is to choose the nodes according to mean fill And when we have two or more nodes that have the same number of filling edges, we break those ties using mean degree. So we're going to select among those nodes that are tied the one that has the minimal number of neighbors. Another possibility is to use first mean degree to select the nodes and break ties using mean fill. But the first one tends to be more common because mean fill tends to work better than mean degree. What the people also do is to use some stochastic process in the combination of the heuristics. And there are two main ways for doing that. The first one is to use always the same heuristic but break ties stochastically. So we can, for instance, use mean degree to select the nodes, but when we have ties, we just like flip a coin and decide which node should be eliminated first. Another and a different way of doing that is to use different heuristics to eliminate the nodes, but the choice of which heuristic I'm going to use in each step of the selection process is done stochastically. So I flip a coin, I say I'm going to use mean fill now, and I flip a coin again, and I decide to use mean degree in the second step and do this process. In the case that we use one of those stochastic techniques, what we usually do is to run those techniques a few times and take note of the best elimination order and use this best elimination order. So remember to run the stochastic a few times and use the best elimination order. And one very interesting idea is these optimal elimination prefixes. So a prefix of one elimination order pi is a sequence of variables that we're going to call tau that occurs in the beginning of pi. So for instance, if we have one elimination order pi that's A, B, C, D, and E, we can have two prefixes, just two examples, like tau A, B, C, and tau A, B, or tau A. These are prefixes because they occur in the beginning of the sequence. And if tau is a prefix for some optimal elimination order, then we say that tau is an optimal elimination prefix. So the idea is that we can complete this prefix in order to reach one optimal elimination order, and the notion of width that we have for the elimination orders, we can extend it to prefix by just considering the cluster sequence that is applicable to the prefix and computing the width of the clusters that we have in the prefix. And why we are defining this idea of prefix is because there are some rules that we can apply that will eliminate a subset of the variables that we have in the network, and it will guarantee that those variables that we eliminate is a prefix for some optimal elimination order. So even though those rules are not complete in the sense that we cannot always generate a complete elimination order, we can at least choose a few initial variables that are guaranteed to belong to some optimal elimination order, and we can later on complete this prefix using some heuristics that we have discussed before, and that is going to discuss in the next slides. Okay, so we're going to present these rules that generate an optimal elimination prefix in the next slide, but before that, let's just clarify a few details. The first one is that we're going to maintain what I call a lower bound low of the tree width. So this lower bound will be updated by some of the rules that I'm going to present, while other rules will use this lower bound as a condition to apply the rule. So we can understand the rules as two sets of rules. There are rules that update this lower bound, and there are rules that use this lower bound as a condition in order to fire the rule. So when we apply one of those rules, what we are doing is to eliminating a few variables. So we can understand those rules as forms of graph decomposition. So we're going to take a graph G, apply the rule, and we'll have a simpler graph G prime that doesn't have the variables that were removed. So if we think that this G prime is the result of applying the rules to G, and low is the lower bounding that was updated according to the rules. So one property that's important is that the tree width of the graph G, the original graph, is going to be the maximum of the tree width of a G prime and low. So low is really a lower bound for the tree width, and the final tree width for the graph G will depend also of the tree width of the graph G prime. So we will continue to eliminate the other variables, check for the clusters, and see which is the larger cluster that we get. So we can say that these rules, they are important because they reduce the computation of the tree width of G into a computation of a tree width of a smaller graph G prime. Why G prime is a smaller graph? Because it is the result of applying those rules. They are removing some of the variables, so you will have less variables than G. But even more important than that is that those rules are guaranteed to generate only optimal elimination prefixes. So it's going to be a good start, and as we finish with those rules, we can complete the prefix to generate a complete elimination order using the risks that we have discussed in the previous slides. And the final definition here is that a simplicial node is a node that all its neighbors are pairwise adjacent, forming a clique. So if you have one node is a part of a clique, it is a simplicial node. And an almost simplicial node is the one that all but one of the neighbors form a clique. So these are the four main rules in order to generate optimal elimination prefixes. So we have two types here. This first rule is a type that updates the lower bound, low, and these three rules here use the lower bound in order to fire the rule. So what are the rules? So we have the simplicial rule. It says that we can eliminate any simplicial node with degree D, updating low to max between low and D. So basically what it's saying here is that we will have initial value for low that is predefined. In this case, low will start with value 1. We cannot have a tree width equal 0. And let's suppose that we find a simplicial node like A that is connected to two neighbors, B and C. So in order to be a simplicial node, it must be in a clique. So in this case, when we eliminate A, we will generate a cluster that mentions A, B, and C. And this cluster has size 3, and according to the width definition, it will have width equal 2, right? So in this case, we can say that in the process of eliminating A, we will have one new lower bound for the tree width equal to 2. So we can change low from 1 to 2. So it's basically what it's saying here. So it's saying eliminate any simplicial node with degree D, and in this case A has degree 2, so D equal 2, updating low to max between low and D. In this case we had a low, it's gonna be the max between what it had low before was 1 and this new D that we just computed that's equal to 2. And in this case now low is equal to 2. And if we had found something that's one structure that was more complex, it could be like A, B, like C, and D. And if we want to eliminate A, because we have this clique, there is no way to eliminate A without creating a factor that we will mention all the variables in the clique, A, B, C, and D. In this case, A has degree equal 3, and low will be updated to 3. So why this is optimal? It's because we cannot avoid, right? So in the elimination order, we need to eliminate all the variables. So we cannot avoid eliminating A. When we eliminate A, we'll have to create this factor that mentions all those variables. So we'll have to update the tree width. So the minimal value for the tree width is 3. It's minimal because it is a lower bound. If we continue eliminating variables, we can find a larger clique. In this case, we will have to update the lower bound to a larger number. And we have these 3 rules here that depend on low in order to be fired. The first one is called almost simplicial rule, and it says that we can eliminate any almost simplicial node with degree D as long as low is greater or equal to D. We have the bud rule that it says that if low is equal or greater to 3, eliminate any pair of nodes X and Y that have degree 3 each and share the same set of neighbors. And the cube rule that if low is greater or equal to 3, eliminate any set of 4 nodes A, B, C, and D, forming the structure that we are showing here in the figure. So these rules are complete for graphs that have a tree width that is smaller or equal to 3. So it means that if we have a graph that have a tree width that is smaller or equal to 3, we will apply those rules in a sequence and we will have a complete elimination order. So we will find to eliminate all the variables using those rules. Okay, the 4 rules that we saw in the previous slide are the 4 general rules, but we can also derive some special cases that are easier to remember and also very common in practice. So there are 2 special cases for the simplicial rule. They are called the Euler rule and the twig rule. So the Euler rule says that we can eliminate any nodes with degree 0, and the twig rule says that we can eliminate any nodes with degree 1. And what is the case? If we start the process with low equal to 1, and if we find the one node that is isolated, so it has no neighbors, it can be understood that it is one clique. It's one clique with just one node. And in this case, we can eliminate A, but the degree of A is going to be 0. So we don't need to update low. And because it's going to be the maximum between 1 and 0, so we will keep our low equal to 1. It's the same thing that happens if we have one node that has just one neighbor. And in this case, we can understand that it is also a clique that is composed by just 2 nodes, and they are connected between each other. The degree is going to be 1, so we can eliminate A. And low, it doesn't need to be updated because the maximum between 1 and 1 is going to be 1. And we also have 2 special cases for the almost simplicial rule, and they're called the series rule and the triangle rule. In the case of the series rule, it says that we can eliminate nodes with degree 2 if we have the lower bound, the low, greater or equal to 2. So for instance, if we have like A, B, and C, it's saying that we can eliminate B if low is greater or equal to 2. And it doesn't matter if A and C are connected or not. If they are not connected, it will be the almost simplicial rule. If they are connected, so we will apply the simplicial rule. But in this case, we would have to update the lower bound to the degree of B, that is 2, but the lower bound is already 2, so the maximum between 2 and 2 is 2. In a very similar way, we have this triangle rule that says that we can eliminate nodes with a degree 3 if low is greater or equal to 3, and if at least 2 of the neighbors are connected by one edge. So it's saying that if we have a situation that have like A, B, C, and D, and we can eliminate A if we have like 2 of the neighbors connected, like in this situation, and low is greater or equal to 3. So it's guaranteed that we can eliminate A. And if they are all connected, so in the first case that we have just 2 neighbors connected, we are applying the almost simplicial rule. If we have again all the neighbors connected, it will apply the simplicial rule. And in this case, the degree of A is equal to 3, but we already have low greater or equal to 3, so we don't have to update low. You may ask, if we don't have these at least 2 neighbors connected, what we're going to have, right? So in this case, we can apply other simple rules that don't even need this requirement of low being greater or equal to 3. So we can think about, if we have just B, C, and D, and have the neighbors are not connected at all. So in this case, we can apply the twig rule and eliminate B, and eliminate C, and eliminate D, and we don't even have to have the requirement of having low greater or equal to 3. In the case that we have a situation that's similar, for instance, we have 2 of them connected, not the 3. We have A with B, C, and D, and we have 1 of those guys connected. We still can eliminate D using this twig rule, and we can deal with A just using this series rule here. And again, we don't even need this requirement of low being greater or equal to 3. Okay, so now let's take a look at one step-by-step example to check if we are understanding everything correctly. So in the previous slide, we saw those special case rules, and they are interesting because they define rules to eliminate nodes with degree 0, degree 1, degree 2, and degree 3. And this is very handy when you are dealing with these optimal elimination prefixes, because we can look at and see what are the degrees of the nodes that we have and see if we can apply those rules or not. In this case, we don't have any nodes with degree 0. We don't have any nodes with degree 1, and but we have quite a few nodes with degree 2. But in order to apply the series rule, we need low to be greater or equal to 2. And we start with a low equal to 1. And in the case that we cannot find any rules that we can apply, we have to increase this lower bound to a greater number so we can apply more rules. So what we can do is start tau is going to be our prefix, and we start with the variable f, with the node f, because f is part of a clique here, and it has degree 2. So in this case, if we start with f, what we have to do is to update low with the maximum value between a low, that is 1, and now 2, that is the degree of f. So we update low to 2 in this case. As we update low, we can start applying the series rule that involves nodes with degree equal to. Let's do that in the next slide. So great, now we are in a very comfortable position because we have low equal to, and we have all nodes here with degree equal to. So it means that we can eliminate any of those nodes, and it will be part of the optimal elimination prefix, and we don't need to update low. That's good news. So we can choose which node we want. I'm going to keep the same order that we had before. So the next node we're going to eliminate is going to be A, and that's going to be the series rule. So we eliminate here A, and we will connect the neighbors together. And so we are applying the series rule, and we don't need to update low. Alright, so now we have this graph here, and we need to decide what we're going to do. Again, we have 4 nodes, all of them with degree equal to, so we can choose any of them to eliminate. I'm going to eliminate B to keep the order that I had before, and it's going to again apply the series rule for doing that. Alright, and now we have to decide which is going to be the next one. Again, all those nodes have degree 2. I'm going to eliminate C, and we don't need to update law, applying the series rule again. That is, and now we have D and E together. And this is the case for the twig rule that can eliminate the nodes with degree 1. Again, we don't need to update the lower bounding. And now we have the node E alone, so it's going to be isolated, and we can apply the Euler rule, and we're going to finish this process. Great. So here it is. We apply the rules because this graph here has a 3 width equal to. We were able to not only find the prefix, but we could find the entire elimination order. And that would be also true if we had a graph with a 3 width equal to 3 as well. So these are great news, and we found the entire elimination order. For more complex graphs, what will happen is that we start applying those rules until we get to a point that we cannot apply them anymore. So it's going to be a prefix, just the first few variables of the elimination order. What is good is that it's guaranteed to be an optimal elimination order, or at least the prefix for the optimal elimination order, and we can continue and finish the elimination order by using one of the heuristics that we have discussed before. The good thing is that now we have a simpler graph in order to feed to the heuristics, so it's going to be a little easier for the heuristics to operate over this simplified graph. Okay, so this idea of lower bounding is really powerful because the rules depend on the lower bound in order to be fired or not. So you would like to have a lower bound that is as large as possible, of course, without compromising the tree width. What I mean is that you want to increase the lower bound, so this low for a graph G should be as high as possible in order to allow the rules to fire, but we still need it to be a lower bound, or in other words, the tree width of the graph G must be larger or equal to this lower bound. And we have two main techniques to set the lower bound. One we have already seen is this first one here. If a graph G has a clique of size n, then the tree width of G is larger or equal to n-1. So it's basically the simplicial rule that have been applied so far. And if the clique has size n, it means that every node is connected to every other node in this clique of size n. It means that because we don't have self-loops, the degree of each of the nodes there is going to be equal to n-1. So that's where this rule comes from. And the second one is the degree of a graph. And the degree of a graph is the minimum number of neighbors that we have in any of the nodes in the graph. So if you look at here at these two figures, the top one, the degree is 2, because we have this node A here with degree 2. So it will be the minimal degree in the entire graph. So the degree of this graph is 2. But for the graph here, at the bottom, the degree is going to be 3 because we have 4 nodes. All of them have a degree 3. So it is this idea of a degree of a graph. It's interesting, but it's also a little bit strange because when you think that as a lower bound, we have this graph here is a subgraph of this guy here, right? And the degree is actually higher than this degree that we have here. But if it is a subgraph, so the tree width for this guy here must be smaller or equal to the tree width of this guy here because it is a subgraph. So what we usually do is to use one alternative measure that we call the degeneracy, and the basic idea of this measure is to decompose this graph here into subgraphs and measure what is the degree of each subgraph. So the degeneracy of a graph is the maximum degree attained by any of its subgraphs. So it tends to be a better bound, and it's based on two observations that I have mentioned before. First, the tree width of any subgraph cannot be larger than the tree width of the graph containing it. And the second one, the degree of the subgraph may be higher than the degree of the graph containing it. So it is this kind of strange relationship that I show it to you, that the bottom graph is the subgraph, the top one, but the degree of the bottom graph is actually larger than the degree of the top one. So if we can decompose the top one into subgraphs, we can find a larger degree and use that as a lower bound. So let's take a look on the next slide for one example. So this is one example of how we can compute the degeneracy, and it also known as a maximum minimum degree, or simply MMD. One good thing about this technique is it is very easy to compute. And if we compare with finding clicks in graphs, that is an NP hard problem, so it becomes even harder as we try to find larger and larger clicks. So this technique is much easier to implement, and it's going to be also a lot more efficient. So the idea is very simple. We start with the original graph and we remove the minimal degree node. And why we remove the minimal degree node? Because we want to find subgraphs with large degrees. So it makes sense to remove the ones that have the nodes that have small degree. And the MMD is the maximum degree attained by any of the generated subgraphs. So we start with the graph. It has degree 2 because of A, as we explained in the previous slide. So I'm going to remove A, and we have this graph here. And now every node, we have 4 of them have degree 3. I can remove n of them, but I register that I have degree 3 here. I decide to remove B and continue. Now everyone has degree 2, and I save that information and move on. I'm going to remove node C, and I have this graph here. Now everyone has degree 1. I remove D, and now the nodes have the node has degree 0. So we take the maximum here, that is this guy, and this is the MMD for this graph here, and I can safely use this as a lower bound for the tree width. Okay, so reminder that the techniques I've been so far, they are guaranteed to just generate one optimal prefix. If you want to generate an optimal elimination order, it's going to be a complete elimination order with all the variables. We needed to expand these ideas with other techniques. One way of doing that is using a systematic search procedure. It's going to be limited to a small number of variables, but we'll see in the next slide that we can speed up using some pruning techniques. But one way of doing this is using depth-first search, and this is illustrated here in this slide. So we know that if you have n variables, if we use depth-first search, we'll have any factorial possible permutations of these n variables. So the search space here is going to be huge. The idea is that basically we have the root node that we start here. We make a first decision. Let's suppose that we have 4 variables. So I have A, B, C, D. I decided that I will start with A, and for A, I have another 3 possibilities that are AB, AC, and AD. That's in this level. In the next level, I will make another decision like A, B, C, and in this level here, going to be A, B, C, D, and all possible combinations here that we can have, right? So what we know is that when I get into a leaf node, I have a complete elimination order. So I need to go until a leaf node like this to have the elimination order. When I get here, actually in n node that I can measure what is the width of this partial elimination order or even the complete elimination order. And we basically do the simulation process where we take the graph and we compute the clusters and see the size of the clusters. We can do that quite efficiently. We don't need to actually eliminate all the variables and do all the multiplications. We can just simulate in the graph the technique and see what is the width. Now, the problem of this technique, of course, is the size of the search space. So we need some way to prune this search space in order to make it a little bit more efficient. So if you want to make this technique of depth first search a little bit more efficient, what we have to do is to put all the pruning techniques together in order to see if we can speed up this search. So one thing that we should do, we should remember the pruning techniques that we saw for Bayesian networks in lecture 7. So if you're working with Bayesian networks, we prune the network in order to reduce its tree width. And we also apply the optimal prefix rules because they will give us an initial optimal prefix, and we'll also prune the graph because it will eliminate the nodes, the variables that belong to the prefix. It will eliminate from the graph. And when we finish with that, we can start the depth first search, and basically this root node here will not be the first variable, but it will be the first variable after the end of the prefix. So we don't need to search for the entire thing. We want to search just for the remaining part of the elimination order. And let's suppose that we have one complete elimination order that we call pi with width w pi. So this is the elimination order that we have. Remember that in order to be a complete elimination order, it must be one leaf node in our search tree. And in order to find this complete elimination order, we don't need to actually search for that. We can use one of the research techniques that we haven't seen before, and we can compute the width of this elimination order using also the techniques that we have seen before of simulating using the graph. And let's suppose also that we are searching this tree and we are in this position here, right? And we have this prefix tau here, and this prefix tau is not an optimal prefix. It's just the initial variables that we are considering, and we are going down this tree here, adding more variables. But before we go down, we can make a test, and its test will be composed by two pieces of information. One is the width of this prefix tau that we are calling w tau, and again, we use the graph techniques in order to compute that. It's just a simulation. We can do that efficiently. And the other piece of information is a lower bound for the graph g tau. So if you look at this point here, we will have a graph that we are decomposing. We're calling this graph g tau, and we can use the lower bound techniques that we saw in the previous slide in order to compute the lower bound for this graph. So this lower bound can come naturally from the simplicial rule, but it can also come from the MMD technique that we saw a few slides ago. And we can make a simple test. We can compare the width of this prefix tau and the lower bound, and we take the maximum between these two. And if the maximum is larger or equal to the width of this elimination order that we already have, so we cannot improve the order pi, and we can just prune these, stop here, so we will not go down in the search tree, and we can go to another, so we can backtrack and go to another branch and continue with the search. So good, this is a nice example how we can use those lower bound techniques in order to prune the search. Okay, I think that is good for now. We're going to have a break now, and we'll continue in the next video when we're going to start discussing the joint trees and relationships to the elimination order. See you soon.